Hello, lovely people. So, today we are doing something a little different. We are going to solve three questions that I faced when attending a placement test. Now, we will solve them one by one. Now, take a look at the questions. So, the first question is this. In the question, we are given an integer array and an integer k, which is the target. In one operation, we can modify any single element of the array to any value. So what we have to do is we have to find the minimum number of modifications that are required so that the OR, that is the bitwise OR of all the elements in the array, becomes strictly less than k. If it is not possible, we can return -1 or, according to the question, 0. So now if we take a look at the given example, here the array is 3, 5, 6. So if we OR the entire array, so 3 will be in binary 0, 1, 1, 1, 0, 1, 1, 1, 0. And k is 1, 0, 0. So if we OR this, we get 1, 1, 1. But we are not going to follow this logic to solve the problem. So what we are going to do is, we are going to see if any of the element in the given array has forbidden bitwise values. So let me explain that. So we all know the OR table looks like this. So to ensure that the OR of all these values is lesser than k, we must make sure that there is no 0 in both these positions, because this is 1, at least 1 should be in this position. So what I mean is, for OR result to be less than 4, no bit can be set where k has 0. So from this representation, we can clearly see in bit 2 any values either 0 or 1 can be allowed, but at least there should be 1, 1 in the values of this array elements. But here, since it is 0, we can only have zeros here. That is, all the elements must have 0 in bit 0 and bit 1. So if we see in 3, it has 0, 1, 1. The bit 1 and bit 0 has 1, so it is an invalid integer. So we have to change, we have to perform some operation on this for it to be lesser than 4. And then when we look at 5, 1, 0, 1, again this bit 0 has 1, so we should perform operation on 5 also. And when we take a look at 6, there is 1 in bit 1, so we have to perform an operation on 6 also. So the output will be 3 operations. That is the minimum number of operations required to make the OR of this entire array lesser than 4. Now if we take a look at the second example, 1 is 0, 0, 1, 2 is 0, 1, 0, again 1 is, we know that, and then k, here it is 4. So here also we seem to have forbidden bits. But before we get into this entire process, we will check the OR of all the values. This, which will be 3, which is already less than 4. So we will return 0. So now let us take a look at the code. So here is the entire code. This is the function name that I have given. So first step, we have to compute the OR of the entire array, and then we have to compare it with the value. So if it is already valid, we return 0. Now the forbidden bits finding part. So here forbidden is bitwise not, that is complement of k. It flips every bit. Here we are using this particular flipping in this problem because we want to find the forbidden bit positions. So for example, forbidden positions are where k has 0 because final OR must not contain 1 there. Then I declare a variable modifications and assign the value 0 to it. Then we are implementing the for loop to check if there are any forbidden bits. If there are any forbidden bits, we increase the counter of modifications and then we return modifications. So I have implemented a few test cases here. So let us see if this is going to run properly. So as you can see, we have gotten the desired results here. So this code works. Now moving on to the next question. So from in this question, the second question, the given integer array, and we have to find if the array is balanced. If it is not balanced, we have to find the minimum number of subarrays that will give us a balanced array. And subarray or an array is balanced if it has only one element or if its last element is strictly smaller than the minimum element of all the previous elements in the array. So we must partition the array into minimum number of contiguous subarrays such that each subarray is balanced, and then we return the total number of array or subarrays. So how do we proceed with this? We use a greedy strategy starting from right to left because we need to check the validity of the last element first. So a subarray ending at index j can include elements to its left as long as the current index is greater than or equal to the last element which is at index j. If we encounter the j is greater than I, that element cannot belong to the subarray. So we must start a new subarray. So the correct algorithm for this would be to start from the rightmost element and then we set a current minimum, that is of the index n minus 1 where n is the length of the array, and then we move left. So if the current element is greater than the current minimum, include it in the current subarray, or else we start a new subarray and update the current min. So we count how many times we start a new subarray. Now let us take a look at the code. So this is the code. So if it is not array, we return 0. Not in array, and then count, we initialize it to 1 and then minimum to the starting value of the array, that is the index 0, and then we go to the range and then we implement the condition here and then we update the current minimum, and then if it is not there we increment the count and then we update the current minimum, and then finally we return count. So now let's try running this. We just change the name. So we can see we are clearly getting the correct values. Now moving on to the next question. So in this next question, we need to find the minimum cost under length constraint. So we are given a 2D array pair where each element is like length and cost, and we are given an integer k which is the maximum length allowed. So we must ignore all pairs where length is greater than k, and for remaining pairs we group them by length, and from each group we choose a pair with the minimum cost, and at the end we sum all the minimum cost and return the value. So now let's take a look at the example given here for better understanding. So given pair is 1 2 3 4 1 5 and 5 6. So here we remove the invalid, which is here length is 4. So here length is 5 at the final index, which is 5 and 6. So we remove it and then we group it. We group it like we add the length first. We try adding it. So it is like 2 plus 1 plus 3, which is 4. So we'll keep it in one group and then we'll group 1 and 5 separately. So the minimum cost in 2 and 4 is 2 and 5. So the output, we group the minimum together, which is 1 and 2 and 1 and 5. So it will be 2, and then we'll group the 3 and 4 separately because length is 3. So if we take the minimum cost, which will be 2, and from the second group, which will be 4, we will get the sum of 6. So now let's take a look at the code. So here we create an empty dictionary minimum cost, and for each length and cost in pairs, if L is greater than K, we skip. Else, if L is not in map, we store C. If not, then we update minimum existing and we sum all the stored values in the map. The map contains all the cost. So if we are finding minimum of that, and we sum all the minimum and we return sum. And the time complexity is O of n and space is also O of n. So now if we run the code, it should be let me save this and then run it. Yeah, so as you can see, the output is properly being computed. So you can find all of this code in my GitHub, which is linked down in the description. So that's all for today. Hope you guys enjoyed today's video. So see you in the next one. Bye bye.